All right, so standard announcement, Money's Point due this Sunday. Everybody's algorithm selection has been kind of graded. I went through, basically made sure it's either on the list or justified. So the next step is the project proposal, this roughly 1-page, 2-paragraph submission. Short, not expecting a whole lot from that. That's due not this weekend, but next weekend, next Sunday. So again, that's a group assignment. Only one person has to submit that. Basically, it says in the assignment what expecting, but first paragraph, give me a description, like your abstract of what the algorithm is, what it does, what it's inspired by, what it claims to be good for. And then the second paragraph, how you're going to work on testing that or demonstrating that. So what is your rough sketch of your demos? We're going to apply this to this problem, this data set, and so on. So that's the goal there. Concept check 5 over this unit 5 physics stuff is this weekend, this Sunday, and then mini project 5 is then due week after that. Questions? So a week from today, this will have to be a recorded lecture, so I'll send a note about that. There's a conflict that I had to deal with. But so we'll still have content, but and a lot of people end up watching the recorded ones anyway, but I'll send a note about that. So that's not Thursday. Thursday's still normal, but then a week from today, so next Tuesday, then that'll be recorded only. Okay, so getting back to this, make sure there's no questions. All right, so we're going to wrap up this unit here. So we're going to finally, culminate in simulated annealing and its sort of now younger sibling, parallel tempering. All right, so last time we talked about that there is a process, a maximum entropy process that is used across machine learning and data science and in modeling that allows you to take constraints and then say what is the maximum entropy distribution subject to these constraints. And if you apply that to a constraint where energy is positive or non-negative and the average energy is fixed, then you get the Boltzmann-Gibbs distribution, which in this case we're considering discrete energy states. And so for every discrete microstate, you can calculate an energy for. And in the Boltzmann, lower energy is better. And so it's more likely for lower energies microstates than higher energy microstates. And so the probability of any microstate is proportional to the exponential of the negative of its energy divided by this scaling constant, this temperature here. So the idea here has been demonstrated, and there's this little app, this little Boltzmann. The idea here is that as you have higher temperature, then you'll get a flatter distribution across microstates. If you have lower temperature, then you'll start to favor microstates that have lower energies far more than those that have higher energies. So we know that there's this proportionality here. So in order to get the actual probability distribution, you just take all of your microstates that are in your outcome space, you calculate all their energies, and then for each one of their energies, you calculate this proportionality term, and then you just sum them all up and normalize, and that sum is what the physicists call a partition function. But it turns out that in most of the ways where we use this, and we'll see this in simulated annealing, we'll see this in the Metropolis algorithm, that normalization factor drops off. And so the only thing we care about is the numerator, the thing you're proportional to, and that's the Boltzmann factor. This formula, though, it is the same formula as in softmax, and so softmax is a tool that sets up a probability distribution at the back end of, say, a neural network, where a neural network is trying to make a decision about a bunch of discrete classes. Is this thing in one class or another class or another? And it builds up enough evidence, and that evidence we view as kind of like inverse energy. And then based on that evidence, you need then a distribution of, okay, well, so based on on this relative evidence for one classification or another, then what classification do you actually make? And then you can set the temperature in your softmax to sort of say, do I want it just a uniform output, which means I'm just going to allow and be a little more playful. So even though the next highest probability word that I could predict might be turtle, you know, then if I set my temperature a little higher, then the lower probability words like dog and cat will sometimes come up. So you can tweak softmax to be more exploratory, and other things based on the Boltzmann. That's the other thing that you're doing with temperature, is that by tweaking temperature, you're making them broader and more exploratory. And that's what we'll see in simulated annealing. It's that by making our jumps from microstate to microstate warmer, we're now permitting jumping to microstates that would otherwise be inaccessible at cooler temperatures. So that's how that whole dynamic works out. So there's a little demo. If you want to play with that, this softmax demo, you can adjust the temperature and watch how it changes those distributions across. You can also adjust the energies or the evidence strengths, the logic scores for each one of these outcomes. All right, so that was our background, that we're going to build off of this. You know, the idea would be that if we can build a Boltzmann sampler, so if we can build something that can sample microstates along with the Boltzmann distribution, where our energy function will be our fitness values, then we can build simulated annealing. That's what we're building up to. So any questions on this? This idea of the Boltzmann is the MaxEnt distribution when you have a fixed temperature and non-negative scores. Okay. Okay, so that's where we were last time. So what was this distribution originally used for? So there was this, so the distribution's been out there. It's been out there since the, I don't know, the 1800s, since Boltzmann. But you know, but what was the idea of sampling from the Boltzmann distribution? Why did people start getting interested in that? So around World War II, there was this group where the lead author of the paper was Nicholas Metropolis. So that's where we're going to get this term Metropolis algorithm. It's around the same time as World War II. And so we also talk about, you know, it's a little confusing. There's the Metropolis algorithm, but there's also the Manhattan Project. And it turns out that a lot of stuff in random sampling actually came out of the effort to build the nuclear weapons. So it's sort of just a coincidence. So the Metropolis here is just a last name, where the Manhattan there was actually Manhattan. But this was Metropolis, and the team were looking for computational methods that they were, they were developing, well, I guess I could say the background context was around World War II, Monte Carlo methods became a very popular technology. So the term Monte Carlo, it was a code name in the Manhattan Project for this idea of solving numerical problems by randomly sampling from them. So Monte Carlo is a group of casinos, and so that's where kind of the name came from there. So they, you know, that was the code name to kind of hide that. And so those methods kind of boomed just after, just around the time of the development of the atomic weapons, because they needed these numerical methods to make predictions about these processes that were going on, so they could then design the technology. And so it's sort of interesting that these randomization methods, like Monte Carlo methods, were coming around where we didn't really even have good random number generators. And so the random number generators that are in every computer now use these, at the minimum, they use these things, I can't think of their names right now, but doesn't really matter. But there were these old the random number generators, like these middle square methods and things like that, that would be like these things where you like generate a 4-digit number, and you take the middle 2 digits and you square it, and then that becomes your new 4-digit number, and you do that over and over again, and hopefully that leads to a chaotic sequence that if you put a decimal point in front of looks like random numbers distributed uniformly between 0 and 1. But these ugly heuristic methods, they were produced sort of awful strings, and so it was very hard to get a good string of random numbers. So it's something we take for granted today, that you can go to your computer and say, just give me a string of 1,000 random numbers uniformly distributed between 0 and 1. That was something that they were still developing then. And so there was a push, though, for more use of randomness in these numerical algorithms. And that was the background context for this. So the classic example of Monte Carlo methods were, how do you estimate a parameter like pi by random sampling? So of course, if I had a perfect circle, I could measure the circumference of the circle, I could measure the diameter of the circle, I could do that division, and I would get an estimate of pi. But where do you get that perfect circle? There are Taylor series expansion methods, or all these sort of mathematical expressions where, theoretically speaking, if you calculate enough terms, then you could get an estimate of pi. But so were there sort of easier ways to do that? And so the kind of in between of those things, where the physical way to estimate pi is to find your perfect circle, measure the circumference, measure the diameter, do the division, get pi. Sort of the more extreme math case was find like a series expansion where it's got like 1,000 terms to, and then if you add another, 1,000 in first term, 1,000 in second term, that as you add terms, you get better and better approximations for pi. Is there something in between that? And so the thought was, well, if you think about it geometrically, let's imagine that we have a circle, like a dartboard on the wall. If you were to throw darts at that circle, you can count how many fall inside the circle and how many fall outside the circle. And you don't even have to have quite a perfect circle, but at least numerically, we kind of know what it means to be inside and outside a circle, even if we can't build a physical circle that's a perfect circle in real life. And so at least numerically, as we're throwing these darts, we can construct effectively a perfect circle, and we don't have to measure the circumference of that circle. We just have to say, are things on the inside or things on the outside? That's something that's easy for us to do. So can we use that to help us estimate pi? Well, we know that the area of the square is 4r squared, because there's 2r, there's an r here and r here, and then there's an r here and an r here. So there's 2r in both directions. So the area of that is 4r squared. Some of you may have seen this before, so bear with me. The area of the circle inside there is pi r squared. So that's, this whole area here, not including these corners out here. So the thought here is that, well, if we consider a dart thrown at this dartboard here, the numerical way, the computational way to do that is to draw a uniform. So if I have the ability to do this, to draw these uniform distributions, if I draw a point uniformly in X, across here, and uniformly in Y across here, then that will be, that is going to land somewhere in this region. Then I can ask, did that point land in the circle? And that's this predicate inside this probability here, this event, this set of outcomes. The probability that x squared plus y squared is less than or equal to r squared. That defines inside a circle. So I know that the probability of this thing landing inside the circle is just the ratio of the two areas. So it is just pi r squared divided by 4r squared, which is pi over 4. So the probability of hitting the circle is an expression that involves pi. So I can just take Borel's law of large numbers, where I say the number of events that occur divided by the number of times I try it. If I do that lots and lots and lots of times, that ratio converges to the probability of the event. And so that means that I can estimate pi just by counting how many of these randomly drawn two-dimensional, how many, I draw an X, I draw a Y, I see, did that fall inside the circle? Yes, no. I calculate, I figure out how many yeses I got, divided by how many total tries, that will be an estimate of pi over 4. And if I multiply that by 4, that'll be an estimate of pi. So that's one of the many ways. There's also Buffon's needle. That was a popular one where you drop a bunch of toothpicks onto a simulated a table made of a bunch of different planks, and you see how many toothpicks cross one of the gaps between the planks versus not. And it turns out you can do a similar geometric derivation of the probability that you'll hit one of those cracks and it will have a pi in it. And so you can then drop simulated toothpicks and then see how many do that. And that's another way to estimate pi this way. All right, so that's just a Monte Carlo method, a way of taking lots and lots of samples so that the ensemble statistics allow you to calculate a quantity without actually going through the ugly process of calculating an integral or doing something like that. So we got to skip all of the math and just got to drop samples and count. Any questions about this example? Monte Carlo estimation of pi. And that all leaned on the ability to do this reliably, to draw uniform numbers. Okay, so what else can we do if we have random sampling? So we're going to move from that estimation procedure where you're estimating a parameter like pi to estimating something uglier, like an ugly calculation, like an integral under an ugly function over a multidimensional space. So the law of large numbers says that if I sample a bunch of times from a distribution, which I'm calling Px, so these are all my samples from Px. So I can call this a proposal distribution, and then I take all of those samples from Px and I divide by the total number of samples. Then as the total number of samples gets very large, then this ratio, this average, this arithmetic mean, becomes an estimate of this integral. And that integral is the definition of the mean of the distribution. So maybe not that surprising, if I sample from a distribution a bunch of times and then take my arithmetic mean, then eventually I converge to the actual mean of the distribution. That's all that's saying right there. But, whereas this equates to this, that maybe isn't that exciting. Keeping in mind that this is an integral means that if I do this right, if I do this process here, I can actually integrate by sampling. And that's what it's going to build up, referred to as Monte Carlo integration. So how do we do this trickery? So more generally, let's say I take those samples and then I run each one of those samples through a function. So I sample a bunch of numbers from 0 to 1, but then before I do this average, I then run them through a function which maps 0 to 1 to some other number here. So I've just got some function of my sample space, and that produces new numbers. If I take those averages of my scaled samples, that thing, by the law of large numbers, converges to this different expectation here. It's the expectation of my function under my sampling distribution, which is written as this integral. Well, this, if you look at that as an engineer, that's something that becomes very useful because this looks like, so this thing is my sampling distribution. And so, it's good. I have to sample from something. This is an arbitrary degree of freedom. So this suggests that if I select this function properly, and I know how I'm sampling, then potentially this formula allows me to calculate any integral I want. I just take my samples, I run them through some function which transforms them, I take their average in the transformed space, and I get an estimate of this integral. And I didn't have to do any cutting things up into pieces and none of the numerics that you normally think of with integration. So how does that look? Well, let's let X be sampled from this distribution, a uniformly distributed random variables between 0 and some length L. And So then the probability, or I guess I should say the density. So this is a probability density for any one of the points in here is 1 divided by L. So it's just a uniform distribution from 0 to L, where the probability density across there is 1 over L across this whole boxcar. So then sometimes we might refer to L as the volume of the support of the sampling distribution, this proposal distribution. Okay, so then if that's my sampling distribution, that's what I'm sampling from, and I take those points and I run them through this function G, then the average value of my G values here will converge to this integral right here, which is just the integral of G divided down by L. So this is similar to like when I threw those darts at the dartboard, I got pi divided by 4, I multiply the thing by 4, and I get pi. So here, I do all of this sampling, I get an estimate of this integral. If I multiply it by my volume, by that L, then I will have an estimate of the integral of G. And G is anything that is defined on this support. So I now have a way to integrate without using traditional numerical methods of integrating up to this point. So the integral of G is just this average here, this L volume divided by M, because I'm taking an average of the sum of these things. And this is the essence of so-called Monte Carlo integration. Now, if you look at that and you squint at that a little bit and think back to how you were first taught about integrals, you're probably taught about Riemann integration. So this idea that you have a function and then you cut it up into rectangles or trapezoids, and then you add the trapezoids together, and then those areas, if they're thin enough, will approximate the area underneath this curve. That's Riemann integration. And then if you took a more sophisticated calculus class, then you might have learned about Lebesgue integration, where you actually the rectangles now go this direction instead of the other direction. So idea here, adding up rectangles. Well, this is kind of adding up rectangles if you think about it, but the rectangles are just positioned at random points. So we can break this up as, well, this L over divided by M, that's like the width of a random rectangle placed underneath the curve. And this is the height of that random rectangle placed underneath the curve. So if I only have a couple of samples, then it's like I'm trying to find the area underneath this curve, and I have this rectangle and this rectangle and this rectangle, and I have a bunch of gap in between them. So of course that's not going to be a great estimate. But over time, I'm going to get more things filling in that gap, and some of them might overlap as well. So I get a little bit of double counting. But the idea here is that once you have enough of those samples, then especially for a well-behaved function, then taking random rectangles works just as well as systematically finding every rectangle underneath that curve. And that's the notion of Monte Carlo integration. All right, so this sets up the context for what Metropolis wanted to sample the Boltzmann distribution for. So that's what we're going to get to here. And then, looking at foreshadowing, the physicists and the chemists are going to have an integral that they really need to calculate. And people had started doing it this way with uniform sampling, but it was taking way too many samples. And so Metropolis realized if you could sample with different distributions, you could use far fewer samples in order to make this work. So that's what we're getting to. Questions on this? This basic idea of Monte Carlo integration. Solving integrals by randomly throwing darts at things. Yeah.
Right now, still haven't gone to the how do you sample from a Boltzmann distribution, right?
Right. So that's what we're getting. So we're going to get to why you want to sample for the Boltzmann distribution. Then the next step will be how do you sample for the Boltzmann distribution, and that will be the Metropolis algorithm. And the next step after that is how to then use it for optimization, and that will be simulated. Okay. All right. So that's Monte Carlo integration. Back to Metropolis. Journal of Chemical Physics, equations of state calculations by fast computing machines. That's what paper was called here. So a little bit of a definition. It's not that important, but there's this idea of an equation of state. This is an invariant relationship among macroscopic state variables. So a famous one you've heard is the ideal gas law, PV equals nRT. It's the relationship when you're at thermal equilibrium between pressure and volume. And so the idea here is that you have a bunch of microscopic state variables that an integral will end up allowing you to solve for these macroscopic properties like pressure and volume. And then hopefully you can then discover these equations of state. So you can say, oh wow, for this ensemble of microscopic properties, it tends to be that whenever we calculate pressure and volume, they relate to each other by this equation of state. So that's what people were looking for there. So if you can calculate macroscopic state variables from models of microscopic interactions, you can look for these equations of state, and those are testable, observable predictions of those microscopic models. So that's the other cool thing about it is, let's say you're not sure what goes on in the microscopic world. If you build a model of what you think is going on in the microscopic world, then you can say, if this is going on, let's look for these consequences in the observable world, in the macroscopic world. So you can say, if my microscopic model suggests that this should be going on. So then, so that's a prediction. So then if you then go into a lab and you can measure pressure and you can also, you can fix volume, then you can say, do we get this relationship that our microscopic model predicted? And if we don't, then that invalidates the hypothesis of the microscopic hypothesis you had. Back to the drawing board, that's not how microscopic particles work together. But if it happens to be consistent, then that gives you evidence supporting what you think might be going on at the microscopic layer. So equations of state help us get from our microscopic theories of the world to macroscopic observables that we can test in the laboratory. So that's why in the 50s, they're really interested in being able to calculate these equations of state as quickly as possible, because they allowed them to test their theories about the microscopic world. Okay, so in order to calculate one of these macroscopic averages, these macroscopic state variables, you need an integral. And so this is the average. So this is the average of a distribution across your microstates of a function of those microstates. So this F function, this is sometimes this mechanical observable, when you just give it a microstate, sometimes it's referred to as this instantaneous version. So there's pressure in this room, but there's also an instantaneous pressure. So you can say, what is the pressure of this microstate? So if you were to take a snapshot of this instant of time and say where all the molecules of this are in the room right now, you can say, what is the pressure at this snapshot of time? And that would just be a function of that one microstate. But we don't experience pressure at an instant of time. We experience pressure across an ensemble of time. And so we feel pressure, and pressure exists over long periods of time, although the microstates are changing among them. And so we feel the average, even though it exists at the instant. So we're trying to estimate the average from a bunch of these instants. And so if we have this instantaneous pressure, and if we have the distribution of microstates, which we've learned at a constant temperature, we assume is the Boltzmann distribution, then if we can solve this integral, so integrate this pressure, instantaneous pressure, along the distribution, the Boltzmann distribution, then we will have an estimate of the macroscopic state variable that we feel. So this was the problem that they were trying to solve. It is a hard problem because the microstates are extremely high dimensional. So normal numerical methods, this didn't work really well for. So like imagine you take that approach to integration that you learned in high school of cutting things up into rectangles. Well, then now you've got not just a 1D space, so this is x1, but now the surface goes out in x2, x3, x4, x5. That's a lot of rectangles. It's just too many rectangles to cut up. The volume is just too large. So that's why Monte Carlo integration looked nice. And so, so you can solve this by randomly sampling from this high dimensional space. But then the question is, how many samples do you need? So Monte Carlo integration, like we just talked about, if we do uniform sampling, then this is the approach that we would do, is that we would uniformly sample from all of our microstates. So we have some volume of our microscope. So it's 3D. This would be a 3D volume. It'd be and so it could be more dimensions than that because you might be sampling not only from position but also momentum. But you sample from the space and then you calculate your instantaneous macroscopic variable, and you then also calculate the Boltzmann distribution's probabilities or probability density here. And you take that product and you take the average of those products divided by n, and then that will give you an estimate of the macroscopic state variable that you want. And that's okay, but I mean, a problem with that is that we're going to need lots and lots of uniform samples for this to converge, and a bunch of those samples are going to be wasted because they're going to be considering microstates that are very improbable. So, I technically have to sample uniformly over every possible microstate in this room. But some of those microstates will be extremely high energy microstates. They'll be microstates that you would not expect in the max entropy distribution. So even though the Boltzmann says it's a very low probability that I'm going to have a bunch of gas clustered up in the corner there, that will be one that might come out as one of my samples. So it would be nice if I only could sample from the microstates that actually had meat here. Because if this Boltzmann density here, or in this case, this Boltzmann probability, if this is low, if this is like 0, then that sample doesn't really exist. So what we'd really like to do is find a way to justify sampling only the most probable microstates and do this integral without biasing it. So how do we do that? So a solution concept is like, well, let's just sample from the Boltzmann, make that our proposal distribution. Don't sample uniformly, just sample so that your microstates that are more common are the ones that are more commonly expected at equilibrium. So we sample from the Boltzmann instead of sampling uniformly, and then maybe that helps us waste fewer samples by concentrating on those likely microstates. So I think I've got the formula for that. So yeah, if I do non-uniform Monte Carlo sampling, so like sampling from the Boltzmann, then now this is my formula. So I can say that, this is the same thing I had before. If this is my Boltzmann distribution, and this is my average, then if I'm sampling from the Boltzmann, then this simple average with no rescaling, this simple average is exactly what I want. So that's the idea here, is that if I'm sampling from the Boltzmann, then I just take whatever samples I get, I run them through my instantaneous macroscopic variable f. I take the average of it, but because I'm sampling from the Boltzmann and not the uniform, then that average converges to this integral where this is the Boltzmann, and that's exactly what I want. So sampling from the Boltzmann theoretically allows me to do this averaging much, much, much more efficiently. But of course, the problem is, how do we do that? How do we sample from the Boltzmann? So that's the problem we have to solve, and that was what was solved in that paper. Questions about this general approach? Yeah.
But you would still need, like, as the number of dimensions go, right? The number of samples that you would need to actually do this, even if you're sampling from the most probable distribution,
right,
would still grow exponentially. Right?
Yeah, right. So high dimensional integration is a hard problem fundamentally. This just makes it a little more manageable. All right. So questions about this? This is the motivation here: is that Monte Carlo methods came up where everyone was using uniform distributions because they figured out how to finally sample from uniform distributions relatively reliably. Now we do it even better. But sampling from uniform distributions, you get a lot of wasted samples. So if you have the ability to sample from other distributions, then you can make these Monte Carlo methods even more efficient. So Metropolis said, gee, how can we sample directly from the Boltzmann? That's what his paper was based on. And it was the first real example, it was the first formal example of what some of you may use. If you've ever taken a class on Bayesian statistics, you've probably talked about Markov chain Monte Carlo methods. This is the first Markov chain Monte Carlo method, and this is why it was put together. Okay, so let's see that. So as a sort of aside, this whole process is a special case of what we call now as importance sampling. Importance sampling comes up in machine learning and training neural networks and things like that too. So the idea here is if I've got an expectation I want to, this is what I would like to calculate, the expectation of some function f under some distribution of x lowercase f here, that's this integral. Well, I can just multiply this density by another density divided by itself, just so long as this other density function doesn't have zero density for any of the places that this has non-zero density. So if this density function, for the support of this density function, if I find another probability distribution that has the same support, so the same wherever this is non-zero, this is also non-zero, then I can just multiply f of x by p of x over p of x. It doesn't change anything, just multiply by 1. So, well, why would I want to do that? Well, if I do that, I can reorganize this. And then now this integral is written a little bit differently. It's the thing that I wanted to estimate times this ratio that we refer to as a likelihood ratio between the density that I wanted to take the average under and my proposal density, my sampling distribution. And then this p of x, or this density function used to be in the numerator, it's now popped out here. And then if I look at that, well, now this becomes the function that I'm taking the average over, and this becomes the distribution I'm using to do the sampling for. So this mean, which is the expectation under this sampling distribution of this, happens to be identical to this, which is the expectation of this uglier thing, which is the function I cared about, scaled by my likelihood ratio under the new proposal distribution. And so this is something referred to as importance sampling. It allows us to, so in simulation modeling, for example, then a lot of times you want to, like, I want to build a simulation of a nuclear reactor. And somebody asks me, how often is this nuclear reactor going to melt down? Hopefully that's a small fraction of operational time. Hopefully it's 0 point lots and lots and lots of zeros and a number probability. But we need to know exactly what the order of that probability is. We need to know, does that have 100 zeros or 1,000 zeros? Because it might be that for our safety factor, if you build a nuclear reactor, it better have 1,000 zeros, not 100 zeros. But it's hard to estimate anything beyond 10 zeros, beyond that decimal point, because it's so rare. If we take our nuclear reactor and we run it for millions and millions of iterations, we may only see one failure. And that may still have so much variance that we won't actually be able to calculate the true probability of that. So we run 1 million iterations and we see 1. We run another million, we see 0. Another million, we see 0. So you might have to run 10 million or 100 million in order to finally get a probability of how often this thing's going to melt down. And your simulation takes 10 minutes to run every replication. And you're not even sure your simulation is a perfect model of reality. So it would really be nice if we didn't have to sample hundreds of millions of times in order to estimate these small probabilities. So what we do in that simulated case is we create a bizarro world where nuclear reactors melt down all the time. They just melt down every day. And so what you do is you set up an internal variable inside that reactor, like the temperature of the day, something you know is likely going to push this thing into meltdown. Something that you can model the distribution of this variable in real life, and you can create a different distribution today. So you know that like the distribution of temperatures in real life is this, the distribution of temperatures in my bizarro sim world is totally different. Has the same support, but we're going to pretty much guarantee that you're going to have really terrible temperature days in the simulated world. Well, under that case, then I'm going to get lots of meltdowns. And so those lots of meltdowns, I can then scale by the likelihood ratio of the temperature in the sim day divided by the temperature in the real day. And that will scale those frequent outcomes down, and the average of the result will actually be the ratio that I want in my world. So that's important sampling, is that it's the ability to only sample the important events and then rescale things so you can actually estimate how frequently those events happen in the real world. So, this, we call this P a proposal distribution. We're going to see that term a lot. We call that ratio a likelihood ratio. It's a correction factor for your sampling. So you can think of this density in the numerator, that's how often the temperature happens in the real world. This in the denominator is how often the terrible temperature is going to happen in our bizarre world. And so this ratio here helps us scale outcomes from the bizarre world into numbers that when you take the average are going to give us the correct proportion in the real world. That's important sampling. And that in the Monte Carlo integration is just a version of this. So we're just choosing a proposal distribution to be more favorable to the sampling distribution of the sampling process. So I've just kind of written that out here that, if you want to estimate this, that's equivalent to estimating this, which is this sampling and averaging process where you've got a different proposal distribution than the distribution you planned for. And that's important sampling and also Monte Carlo integration. So if you set your proposal distribution to the sampling distribution in the real world, then we recover the Metropolis approach. And so you can think of like Monte Carlo integration, we're always going to use uniform regardless of what's going on in the real world. Uniform might be worse than the real world in terms of sampling. In important sampling, you're finding some distribution that guarantees you like the fewest number of samples possible to get the answer. And in this Metropolis approach to Monte Carlo integration, they just picked their proposal distribution to be the Boltzmann distribution because they thought that would be just a more sampling efficient. So you can choose lots of proposal distributions. They chose the Boltzmann and then said, let's figure out how to sample from Boltzmann. So it's a little bit of an aside, but just know that Monte Carlo integration is under the larger umbrella of so-called important sampling, which if you do a lot of time series stuff or simulation work, eventually you'll find that as being a useful tool. All right, so how do we sample from the Boltzmann Gibbs? So before we get here, any questions so far about the motivations? Monte Carlo integration, where we're, as engineers, the only tool we're left with, the only thing we need to figure out how to do is how to sample from the Boltzmann, and then bonus, how to sample from anything. But if we can at least start with how to sample from the Boltzmann, we'll be in really great shape. Okay, so Metropolis algorithm, like I said, it's one of the first. There were technically, if you look back at history, other things that could be called MCMCs, but this really kicked off MCMCs and really revolutionized Bayesian statistics. So Metropolis algorithm. So we have a desired sampling distribution F, which in Metropolis cases was Boltzmann Gibbs. So the algorithm starts by choosing a random microstate configuration. And remember, we're trying to draw microstates from this distribution F. So we now propose a move from this random by random displacement. So you can imagine I just draw a zero mean normal perturbation to this initial point. So I'm going to call that D. So you can imagine that D could be normally distributed, or I could have a general process here of coming up with a new sample based on the previous sample. And in the original vanilla Metropolis algorithm, this function here, this conditional distribution, had to be symmetric. So it was just easy enough to think of it this way, where I'm adding some zero mean perturbation, where this is being drawn from, let's say, a normal distribution with mean of zero and some standard deviation that's up to you. So Metropolis, like I said, D must be symmetric, but for later, I think 70s or something, Hastings came around and adjusted the Metropolis algorithm in a couple of minor but important ways that allowed for this proposal distribution to be anything, asymmetric as well. And I'm not kind of going outside of the scope of this. I want you to know for this class, the difference between Metropolis Hastings is that the proposal distribution in Metropolis Hastings can be generic, whereas it's forced to be symmetric in Metropolis. That's the key innovation. Once you have that innovation, it turns out that you can further optimize the Metropolis approach so that it performs more efficiently, needs fewer samples, gives you better results, and so on, if you can engineer clever proposal distributions. But to just get it work, a nice, simple, symmetric distribution is fine. And that's what Metropolis did. Okay, so we've drawn a point, a random point, and now the question is, do we use our original point? Do we stay at our original point? Or do we spit out the new sample that our proposal distribution has given us? So we need a notion of acceptance. So we accept our new point, and so I'm using prime as my new indicator. So x prime is new, x is the original. So imagine x is the sample we just gave, and we're saying, do we spit out a new sample, or do we just keep going through this process? So accept x prime, our new sample, with probability, and then this minimum here, which basically is saying calculate this likelihood ratio, where it's the density you want. So this would be the Boltzmann distribution evaluated at x prime divided by the Boltzmann distribution divided at x. If this thing is more than 1, then you take x prime. That's all this minimum says. But if this ratio is less than 1, that means that the density at your new point is slightly less than the density at your old point. So now you only take the new point with some probability. So this allows for you sometimes going in the wrong direction, but the probability of you going in the wrong direction, if we're thinking about this as an energy minimizer, is going to get less and less and less based on the difference between the density of your current and the density of the old one here. So this is for generic distributions. If we make this focus on the Boltzmann, then this function, this acceptance ratio, maybe makes a little bit more sense. So if I plug in the Boltzmann distribution for f here, then the ratio I get is this expression here. So this is just e to the minus delta E over kT, where delta E is the energy difference from my new point to my old point. So all this is saying is that if my new point, well, so what the minimum here, which is sort of hidden here, is if my new point is at lower energy, I just go to that point. If I have proposed a point that happens to be lower energy than my current point, take it. That's my new sample. But otherwise, if my new point is some delta E above my old point, then the distance above my old point is going to scale the probability of acceptance. So if it's very, very high, lots more energy above my old point, then it's likely that I'm just going to reject it and just keep my old point and then recycle. But if it's not that far away, then there's some appreciable probability that I'm going to take it, and I'll move uphill in terms of energy, but I don't do that often. And how often I do that depends on my temperature. So for high temperatures, it's very likely to propose samples that are higher energy, even though you're at a lower energy sample. For low temperatures, if you found a lower energy sample, then it is unlikely for you to propose new high energy samples. And so that's our acceptance, except if the delta energy is less than 0, otherwise with this probability alpha. And then that temperature gives us an energy budget, which acts almost like a threshold, a soft threshold on delta E. And then we repeat from number 2. So we have a sample we've proposed, then we go through a bunch of proposals, eventually find a proposal that we accept, then we propose that sample, we do that again and again and again, we propose more, and over time, then, so this is a Markov chain. So every sample, the next sample is going to, there'll be a transition probability from any current sample to the next sample, because everything's kind of anchored together, because you start at a certain position and you perturb off of it. So you can think every output is a state of a Markov chain, and the next output is a bunch of the possible accessible states from that state. So this is a Markov chain, but it's also a sampler where over time, the output of this will converge in distribution to F, which in our case is the Boltzmann. So after a so-called mixing time, then the distribution of values that comes out of this process will match the F distribution. And so that won't happen for the first few samples. So you got to let this thing go. But after it comes to equilibrium, this is a little bit like watching the second law here. So you initialize it at some initial state, and then you sort of let this random process go. You use energy to sort of filter out all of these different proposed samples and accept some of them, and eventually you come to some distribution, and you're still going to be sampling randomly, but the randomness, if you take a histogram of the randomness coming out of there, it's going to match this F. So the difference between that and there is the so-called mixing time. And so, if you have the ability to engineer clever proposal distributions, which is what Metropolis Hastings allowed you to do, you can reduce that mixing time. The mixing time is the time it takes for you to forget your initial conditions. So in this room, if I pushed all the air up into the corner, then for a small amount of time while the room was mixing, you could tell that the initial conditions were the air was up in the corner. But eventually the air locks into an equilibrium distribution where it's still moving, but I can't tell that once upon a time it was pushed up into that corner. And that's what we mean by converging in distribution, and that's what's happening inside the Metropolis Hastings algorithm. Questions about that? Metropolis Hastings allows us to set a temperature and sample from the Boltzmann at that temperature. It really allows you to set any distribution and sample from any distribution. Now, like I said, this revolutionized Bayesian statistics, allowed for these first MCMC methods. So why is this useful? It's useful when sampling from multidimensional distributions because this acceptance ratio gets rid of the normalization factors in your distributions. So the hardest part about sampling from distributions is making sure that the area underneath those distributions sums to 1. And so normally when you create a sampler, you have to normalize all your probabilities. Like if you say, well, I've got 1,000 outcomes, and this outcome is twice as likely as this outcome, and this outcome is half as likely as this outcome, and so on. You have to take all of those relationships and then figure out, okay, so what's the probability of each one, and what's the probability proportional to for each one of them, and then divide by that partition function in order to figure out the actual probability. So in the good old days of sampling, If I could assign, I could say A has a 30% probability, B has a 70% probability. Well, then I could draw a uniform number and I could see where it landed between 0 and 1, and I could map that whole interval to whether we get an outcome A or outcome B. But I had to know the probabilities in order to figure out how to shove them into this interval. But now we have a way where all we care about is the proportionality in probability from outcome to outcome. So we don't actually care about the normalization anymore. And it doesn't sound like a big deal, but if you're talking about a multi-dimensional space, if you need to figure, if I know the density shape, if I know the shape of the density function that I want the sample from, integrating under that, like figuring out how to scale that properly so that it's a probability density, means taking a really ugly integral. But because I'm going to divide by another density, which is normalized by the same thing, then I actually don't care about the normalization constant. I can just cancel it out. So even though I'm sampling from a density function, my acceptance ratio can be based on something that's just proportional to the density functions. So this became really helpful because for like Bayesian statistics, you have a prior distribution on information, on something you're trying to estimate, and then you have some likelihood function that says, given that I've observed this data, what's the probability that my parameter is in a certain range? And so I kind of combine those things together, but I don't actually need to know the distribution of the data that I'm sampling anymore. So it's a way of sampling from a posterior without actually having to calculate the area underneath the posterior. And that made these methods enable Bayesian statistics. So you couldn't solve for a mathematical formula for posterior distribution. So you could say, my prior information was this, I gathered some data, and then after that data, I got the shape of, my new distribution was this. So I used to think these were my parameters, they could fall anywhere in here, but now I know my parameters fall in this narrower range right in the middle here. Well, with pen and paper Bayesian statistics, you would solve for the shape of this thing. But that's hard to do in general. Now I don't solve for the shape of this thing, I run my Metropolis algorithm 1,000,000 times or 1,000 times, and it gathers points. And then a histogram of those points will end up, so now I'll pretend like that was there, a histogram of the points from my Metropolis algorithm will end up being my posterior distribution. So now I can empirically estimate posteriors, and I can fit something to that. So I can't mathematically derive the posterior, but I can sample from it, and if I get enough samples, I can estimate. And that really is powerful, because a lot of times we don't care about the formula form, we just want to know if we thought all of the values were in this range, but we gathered in some data, and now we know they're in this range. That's usually the useful thing there. The downside of this, though, is that these MCMCs, they're Markov chain Monte Carlos, which means that every sample is dependent in some ways on the previous sample. So if I go to the computer and I say, draw a random number between 0 and 1, and then I draw the next random number between 0 and 1, every one of those is independent from the previous one, or they've been designed to be independent. So I can't predict the next die roll from the previous die roll. That's what we want. When you're playing a board game, you roll die. You want to make sure that if it comes up a 6 on this run, then the next run, it's still equal probability across all sides of the die. That's what you want. But in an MCMC, if you know it comes up 6 on the first draw, you actually now can use that information to figure out a restricted set of outcomes for the next draw. And this is kind of like, imagining that little proposal point X as it's floating around, it's here, and then you propose these different options to move around, and you might accept one of them. But, all of these options are close to the original microstate. So if you roll a 6, it's more likely that maybe the next time you're going to roll a 7. Now, over 1,000,000 rolls, you're going to get the right distribution. but the order of those rolls is going to be sorted. So it induces a sorting in your outcomes to keep the outcomes close together, and that's the downside of MCMC. But Metropolis Hastings allows you to use clever choices for your proposal distributions. The Metropolis algorithm, those proposals had to be symmetric. If your original point was here, you had to choose a symmetric distribution of test points around there. But Hastings allowed you to say, I can choose any, like I can bias this search. So for this point, I'm actually only going to propose things going in this direction. For this other point, I'm going to propose things only in these directions, and so on. And so this opened up a new space for designing better proposal distributions for MCMCs. And those better proposal distributions would mix faster, and they would reduce the dependence between samples. It didn't fix it completely, but it made it so that you could run these things and be more confident that you would get this independence. Before that, people used thinning, which would be like, I draw a sample from Metropolis, then I draw 100 samples and throw them out. And then I draw the 101st sample, and that's my next sample. And then the hope would be that there'd be a correlation length that you would have gone beyond, so that the first sample and the 101st sample would not be correlated. So that if you jumped every 100, then you'd get these independent samples again. But then you have to waste all of that time. And so that's why Metropolis Hastings, with it, arbitrary proposal distributions, was so powerful, is that it allowed for MCMCs to reduce some of these downsides. Questions about that? Got the Metropolis Hastings giving us the tools that enables modern Bayesian statistics. All right, so then we can now finally end this unit on our two target algorithms, simulated annealing and parallel tempering, which are just applications of Metropolis Hastings, really just Metropolis. So simulated annealing, remember we're going to take this. So Metropolis Hastings is just a sampler. You give it a distribution, it gives you points that are sampled from that distribution. Their histogram will look like the target distribution. That's what Metropolis Hastings is all about. How do we use that for optimization? And the thought was that, you know, people who work in materials know that you can heat things to particular temperatures, and that you make them, they're more fluid, their microstates more fluid, and then if you cool them, then you can cool them into lower energy configurations, purer configurations. And that was the idea here, is maybe we can do the same thing here. Maybe we can sample from microstates that explore a space fluidly and then cool it slowly enough, and then maybe they'll be more likely to settle into low energy configurations or high fitness configurations. So we need 4 ingredients to make simulated annealing work. The first 3 are basically just a translation from an optimization problem into Metropolis Hastings. So we need a description of our system. We've been doing this for genetic algorithms or whatever. We need a structure of the decision vector. So we just need to define microstates in the system, which for us is designing a decision vector. So this guy is going to be the number of wheels on the car, X1 is the number of wheels on the car, X2 is the fuel type, X3, et cetera, et cetera. So we design that decision vector, a concise description of the system. A random generator of moves. We need to be able, this is like a mutation operator. We need to be able to get from one configuration to another configuration. We need to propose changes to those configurations. A quantitative objective function. We need that instantaneous macroscopic state variable. So we need our objective function. We need to say, we're going to maximize the speed of the car. We're going to minimize the weight of the car. So something that we can translate into an energy defined over all of our decision variable or decision vector configurations. So all of that is basically what we just need for Metropolis Hastings for a Boltzmann Gibbs sample. So then what we add into it for simulated annealing is an annealing schedule of temperatures and lengths of time. So we're going to run the Metropolis algorithm at one temperature for a length of time, and then we're going to move to another temperature for a length of time, and move to another temperature for a length of time. We do it over and over again, and eventually once we get down to our coldest temperature, then the output, which hopefully has settled down because it's cold, that single microstate that comes out of that, that will be our proposed solution to our optimization problem. So let's, so I've shown you this demo on the side here. So, but if you'd like to play around with it, it's the link to it. It's also on the Canvas site, but here's the pseudocode, which also on the Canvas site, you can find a little cleaner pseudocode for this. Generate an initial configuration for our microstate and calculate its fitness, which I'll use as capital F here. Beta is going to be the time I sit at each temperature. So let beta be the number of new solutions until thermal equilibrium. So I'm going to start from 1, and I'm going to keep proposing new solutions at that temperature until I move down to the next temperature. So then I start my loop. And so while not termination, so this termination might be based on temperature. Like it might be that once I hit what I'm defining as the coldest temperature, and I run for beta time steps, I just stop there. You could make it based off of something else, like you could allow this thing to run for longer, but very often in the simplest essay, it's just based on the annealing schedule. So, you've cooled it, it's cooled enough, you cool it out, and that's you done. So while we're still, before that, we're going to iterate through at this temperature, we're going to go through how long we want it to sit at this temperature. So for J equals 1 to beta, where beta is how long we're going to sit at this temperature. We generate a proposed microstate, a proposed configuration of our system, and we calculate its fitness. Then we compare it. So we're going to set, we're going to take that new one as our current state with this probability, which you should recognize from the Metropolis or Metropolis Hastings algorithm. So we use the Boltzmann factor here. So we've got the exponential minus, and this is our delta E. So I guess I could scribble that in just as a reminder. I didn't mean for that to be dashed, but it's kind of a nice effect. So we look at the delta E. We look at does this new one go up in energy or down in energy? If it goes down in energy, then this thing is going to be greater than 1. So this you'll just take it 100% of the time. But if it goes up in energy, then this thing will be less than 1. And the higher it goes up in energy, then the lower this probability will be. The relationship there between energy and probability will be set by our temperature, which I use here, I call lambda. One you can think of it as T. We get rid of the Boltzmann coefficient, or you can think of it as it's in units of Boltzmann coefficient if you really want it to be tied to physics. But we just get rid of that little scalar because it's not doing anything for us computationally. And then we end that loop. So we iterate beta times at that temperature, and then we decrease the temperature based on an annealing schedule that we set. These are common examples of how we decrease the temperature. So the next temperature is the old temperature minus some hyperparameter times the current time. So the current time is the number of iterations through the while loop. So if after one iteration through the while loop, we go down 1 alpha step, 2 alpha steps, and so on. And this goes all the way down until we hit some 0 temperature. Alternatively, we can contract the temperature in this relaxation formula here, where we just multiply by some alpha hyperparameter to the t. And so if t is equal to 0, we have our top temperature. If t is equal to 1, we are effectively we're dividing the temperature down geometrically. So those are 2 common schedules, but you can come up with others. And that's basically it. So that's simulated annealing right there. It's just doing beta draws from Metropolis Hastings at a particular temperature, decreasing the temperature in a predictable way, and then doing another beta draws and doing that over and over and over again until you get to your coldest temperature. Then you end the algorithm, and whatever X is remaining is your optimizer. Questions about that? Yeah.
Why is, like, you mentioned about the multimodal optimization? How?
Yeah, so if you set your final temperature to something that is less than really, really cold, like in particular if you set it to like, 1, then, or not necessarily exactly 1, but if you give it something where it has a little bit of energy, then and you let this thing run at the final temperature, and rather than just stopping it, then what you end up getting is a sampler that is going to be more likely to be in the low energy troughs of your energy function into the peaks of your fitness function. So if you then collect those samples over time, then you've got an approximation of a multimodal optimizer. So you're basically leveraging the fact that this is built on an MCMC sampler and use that so it should stick around those low energy points more often, so then you can turn it into a multimodal optimizer. But then that actually lets me transition, and I just at least want to mention parallel tempering, and because this is the last slide. And then I can start here so that it's not rushed through it, but I at least want to introduce you to parallel tempering. The alternative approach, if you've got the parallel resources in particular, it doesn't have to be parallel, but if you've got the computational resources, then you can get rid of annealing the schedule entirely and instead set up a bunch of parallel Monte Carlo or parallel Metropolis Hastings at a ladder of different temperatures. And you have them exchange at a different amount. So rather than me maybe, I'll start here, but let me at least run that demo to show you what that looks like, to give you some idea. So this is our parallel tempering idea here. So the thing is here, we're now running 4 Metropolis Hastings samplers at single fixed temperatures. And these temperatures are multiples of each other. So basically you multiply by 5 to get from the lowest one to the hottest one. This lowest one's called the cold chain. So we're going to run these things, and I'll just run them at a neutral swap frequency. And the global minimum is down here. You see 4 different little balls at different colors. Those correspond to these 4 different temperatures of the Metropolis Hastings here. Periodically, adjacent temperatures will evaluate whether they should swap. And they use basically a Boltzmann factor, but it's technically a product Boltzmann factor, to decide whether they should swap from each other. So the high temperature one is exploring all the time. But it will then periodically, and you set how frequently. So this is very much like distributed genetic algorithms or island models. It's a migration model, really. So periodically, the one at the highest temperature looks at the one at the next lowest temperature and says, hey, how do we compare? If it happens to be that the high temperature one happens to find a microstate at lower energy, they swap 100% of the time. Otherwise, they swap with a probability based on the difference between their energy levels. And you do that at every pair of temperatures. And then you only sample from the cold chain. And notice the cold chain got stuck in the global minimum. And so you can turn this into an optimizer. You can also turn this, if your cold chain has a temperature close to 0, this is an optimizer that's constantly exploring in the background and telling you the best it's found in the foreground. If you set your cold chain temperature to 1, this is an MCMC sampler that has much better mixing time because it's got a high temperature going in the background that is sort of trying to mix as fast as possible, but then a low temperature that is trying to sample more faithfully from your distribution. Because remember, high temperature is uniform distribution. Temperature equal to 1 is the distribution you want. Temperature equal to close to 0 is just sort of deterministic. So we'll start here at the start of next, on Thursday, just so we don't have to rush through this. And then otherwise Thursday, we're gonna start the next unit on swarm intelligence. So if you have any questions, feel free to come up. Otherwise, I'll see you Thursday.